Bismillahirrahmanirrahim. Assalamu alaikum students. So this is an introduction to MATLAB. I have uploaded a set of videos already, but there were a few topics that were left and I thought that you need to go through them too. So we would cover them inshallah and we'll try to implement them on MATLAB as well. So the references include the Control Systems Engineering 6th edition book by Norman Nice, which is your course book, and the objectives are to learn to use MATLAB, the basics of MATLAB and the basic commands of Control System Toolbox, and we need to learn about the LTI models as well. So basically, what's a transfer function? Transfer function is a mathematical function relating the output of a response of a system such as a filter circuit to the input or stimulus. Mathematical model gives the mathematical relationships which relates the output of a system to its input, and the function, the transfer function, is basically a mathematical function that relates the output or response of system, like for any appliance or any component, to the input or stimulus. So what's system modeling on MATLAB? The Control System Toolbox offers extensive tools to manipulate and analyze linear time invariant systems, LTI systems. It supports both continuous and discrete time systems. In addition, systems can be single input, single output, SISO or SISO, or multiple input, multiple output, MIMO systems. But before moving on with Control System Toolbox commands, let us revise a few mathematical commands which are going to be used in this course. So let's move with the polynomial command. This is a command that makes a polynomial with specified roots. So that's happening when you know the roots and you have to make a polynomial from them. So let's see an example for this. We can go back to MATLAB. Here CLC, and then we'll move forward. Okay, so here we have R as I can specify it to be 1, 2, 3, 1 to 4, and you can see a vector R has been created, and I'll suppose them to be 3 roots. And now to make a polynomial X from these roots, which I have supposed to be 1 to 4, I write it like this. Now you can see that X, a polynomial, has been created, and this polynomial is a third order polynomial, and you can see that we had 3 roots, and the polynomial that has been created has 4 coefficients, which means it's a third order polynomial. Now another way to write this is X is equal to poly, and you can simply copy this matrix vector over here that contains the roots and paste it over here. So I have not used the R function over here, R variable over here. I have directly inputted the roots. You should remember these brackets that I have inputted over here. So I'll just press enter, and you can see that we get the same result for the polynomial. The same way we'll move toward the roots command. The roots we get through roots command exactly. R is equal to roots. So let's move with them. Let's see that this is the polynomial X that we have extracted from our previous task. Now if we want to have roots from it, we can see, and we'll just move the name over here. C is equal to roots of X. X is the polynomial that we got in the last command, and I'll just press enter, and you can see that the roots that I got are 4, 2 and 1, and they are exactly the same roots that we had initiated our system with. So roots is the opposite of poly command. It gives us roots of the polynomial over here, and polynomial poly gives the polynomial from roots that we specify. So these are the 2 commands regarding rational expressions. Number 3 is the convolution and polynomial multiplication. If you need to convolve 2 vectors u and v, you will just use convolve PB into P2. That's, I guess, some mistake over here. This P2 should be here. That means that P2 is this, and it is basically multiplying a vector P with itself. So you can do it, as well as you can use the static command. So let's see that if we have A is equal to 2 and 3, and B is equal to 3 and 4. Now if I use the convolve command, conv A comma B, then I have the result in front of you, 6, 17, 12. And if I use the static, I get an error. Why? Because this is a 2 cross 1 matrix. This is again a 2 cross 1 matrix. One row and two columns, 1 cross 2 and 1 cross 2. So they can't be multiplied. So that's the point. If I apply A dot static B, then we can see that we get 6 into 12. Dot static means that it would point to point multiply the vector. That is, it will multiply 2 with 3 and 4 and 3 with 3 and 4, and then sum them to 2 points. So these are the convolve, static and dot static commands, and the convolve command is used for 2 vectors. And when you need to multiply, you by point, you will use dot static, and if you need to multiply them like vectors, then you will use A static B hyphen. What does this hyphen mean? This means transpose, and you can see that this gives me 18. So if you transpose this B and multiply then it with 2 and 3, which is the A vector, you can see that the result would be 18. So these are some multiplication commands that you can make use of. Now we move further to the residue command, which gives the partial fraction, expansion and polynomial coefficients. So the residue command basically splits the partial rational expression into its partial fraction, and it's a toggle command. It depends on the inputs and the outputs, the number of inputs and the outputs that you declare, that how should it function. What do I mean? I mean that if you are mentioning 3 outputs and 2 inputs to this command, then it will give you partial fractions, the R's, the P's and the K's at the output. And if you are mentioning 2 outputs and 3 inputs, 3 number of inputs and 2 number of outputs, then what it would comprehend would be that it would convert a partial fraction to a rational expression. So we can go on with an example. You should know that the RPK means the roots, the poles and the gain K, the DC gain K. So R is basically the root that would be of each partial fraction. P refers to the poles of each partial fraction, and then K refers to the DC gain. Similarly, B and A is simply this numerator and the denominator. So let's have a look over here. So we'll just use the residue function over here. Let's see that we have a transfer function minus 4s plus 8 divided by s squared plus 6s plus 8. So this is the transfer function, or you can say that the rational expression that we need to divide or distribute into the partial fractions, decompose into the partial fractions. So as I've shown you, it's minus 4s plus 8, the numerator. So the numerator becomes b is equal to minus 4 and space 8. Okay, so I'll just mask it over here, and a is equal to, you can see 1, 6 and 8, and I again, sorry about the wrong bracket. So I've just mentioned the b and a for our inputs and for the rational expression. Now we need to convert this to the partial fractions, and we'll just use the R p k, and then the residue, and now a b comma a. So you can see that we have two roots and two poles, and the DC gain is empty bracket. So the partial fraction that's being made from here is in front of you. Yes, so this is the partial fractions that we are getting it from here. Now to get the real expression back from the partial fractions, to do the opposite thing, what we will do is that we know that r, p and k have already been initialized, and what we'll do is that we'll write the command b comma a is equal to a residue. So now we want a rational expression at the output, and we are giving as input the r, b and k. So I'll just press enter, and you can see that we get the same numerator and denominator again that we had inputted the first time initialized. So the residue command acts as a toggle. It gives back the rational expression from partial expressions and the partial fractions from rational expression. So you have to implement this as well. Now let's talk about the LTI models. So LTI models can be specified as transfer function, zero pole gain model ZPK, and state space models SS. So what's a transfer function? SISO transfer function, single input single output transfer function, can be mentioned as a rational expression in S domain, and you have an example over here. Let's implement it over MATLAB. Let's see that a is equal to TF. This TF over here mentions that we are going to write a transfer function, and then you'll mention in the first bracket the numerator, and in the second bracket you'll mention the denominator. It's the same way that we declared the b and a in the residue commands. So here I write 2 3, and here I write 1 1. This means 2s plus 3 is the numerator and 1s plus 1 is the denominator. Let's see, I'll just press enter, and the transfer function, it's getting a bit delayed I guess. Okay, a is equal to 2s plus 3 divided by s plus 1, and you can see that it has recognized it as a continuous time transfer function. So this is what now you needed to know about the LTI transfer function as a rational expression. A is equal to 2s plus 3 over s plus 1. Now what about the ZPK, zero pole gain transfer function? ZPK transfer functions are of the form given to you over here, that it can be like, there can be a DC gain 5, 4, 10, 20, 100 or any other value, and then there are the zeros. Zeros are the system where the system are the points of the system where the system gets a zero value, and the poles are the parts of the equation, the roots where the rational expression would get to infinity. So s minus z1, s minus z2, s minus z3 are all the zeros, and s minus p1, s minus p2, and p1, p2, p3 up till pn are the poles. So let's declare a transfer function with ZPK model. I'll CLC so that we can move above, and now you can see that I'll declare z is equal, I can even move them without declaring. So e is equal to ZPK. Let's suppose that I have two zeros, 1 and 3, and then I have two poles which are 2 and 2, and let's suppose my gain is 1. Okay, just look at the way I've initialized them. I'll just press enter, and you can see that s minus 1, s minus 3, it's the numerator that we are having, and the two zeros at 1 and 3, which I have already mentioned. Then we have two poles I have mentioned at 2 and 2, so it would be s minus 2 into s minus 2, which is basically s minus 2 square, and then the gain, which is 1, and it doesn't need to be mentioned over here. We can even change it to be 2, and you can see that 2 appears over here. So that's for the ZPK model. You can also convert this ZPK model to transfer function model. How? I'll use A is equal to TF of A. Okay, so let's see what happens. Okay, so you know that you can see that this ZPK model, the expression that was in factorized form, has been converted to transfer function form through this command, and now this can be converted back to ZPK model using this command. I'll press enter, and you can see that this rational expression has been converted to the factorized ZPK form of transfer function by using this command. Okay, so we move back to our manual. This is the state space model. We'll discuss it separately in a coming lab, in lab 3 or lab 4, I guess, so you don't need to worry about it. We'll discuss it over there in detail. So this is about data retrieval. You don't need it much in the lab, but you should know about it, that what does it mean. So if you have to extract the data from a transfer function, how would you do that? This is the command that you need to write. Okay, so I'll just paste it over here. You can see this red line. It doesn't need to be like this, so I have replaced them with single inverted comma. Here you will write the name, which was A for our ZPK model. So I'll extract the numerator and denominator from here in square brackets, and here it is. So I'll just press enter, and you can see that the numerator and the denominator have been extracted out from the transfer function A that we had created, and we can click on A over here to get the value of A. We can also mention A over here. I guess my system is taking some time to proceed. So I'll just press A over here, and you can see that the A was 2, S minus 3, S minus 1, S minus 2 into square. So we have numerator and denominator over here, which have been extracted from the TF data A. So that's just a command to extract data in form of ZPK, numerator, denominator, or the state space from any system. So that's the conversion that I've already told you guys, the explicit conversion. It's the automatic conversion, which is a little difficult, that you have to extract the data ZPK and then to convert that ZPK to the model that you want it to be. So then we have the operations that we need to perform on the LTI models. These are the addition, subtraction, multiplication, right matrix divide, left matrix divide, inverse, per transposition. This means transpose of a matrix. This is transposition. It means point-to-point transposition, and this means the power. Okay, so these are the lab tasks. You don't need to perform the pre-lab, you need to perform the lab tasks, and I guess that's pretty much clear. What I've already told you, it says use MATLAB to find P3, P4 and P5 without the polynomials. So you just need to use the MATLAB commands to find the P3, which is basically the sum of P1 and P2, and then P4, which is the subtraction between P1 and P2, and then the P5, which is a multiplication convolution between P1 and P2. So like this, you need to use only one command to convert P6. And what is basically P6? We can see over here that P6 is S plus 7 into S plus 8 into S plus 3. So you'll just declare it in MATLAB, or convert it or multiply it. You can use any command to but you need to use only one command to calculate this polynomial. Similarly, you need to use only two commands to find g1 of s and plab 3a represented as a polynomial divided by a polynomial. So basically 3a is this zpk and you need to convert it to tf. I guess they are pretty much easy, so I hope that the things are pretty much clear to you now. You have to perform all the tasks. Still, if you face any difficulty anywhere, you can mention it out and I'll be there for you, inshallah. So take good care of yourselves. Allah Hafiz.